Welcome to practical number 13 of subject applied electronics. The practical is regarding class B push-pull amplifier. Myself Sanjit Kumar Singh, lecturer in electronics and telecommunication department at Praveen Patil Polytechnic, Bandar. So this is the circuit to be implemented. Here we are making use of two transistors, one is NPN and another PNP. And the resistors are used. R1 is 3.3 kilo ohm and R2 is 33 kilo ohm. Two resistors are used, 33 and 3.3 kilo ohms. This is the table in which we have made use of transistor BC547 as NPN transistor and the other BC558 as PNP transistor. Now, a push-pull amplifier is an amplifier which has an output stage that can drive a current either direction through the load. Push-pull amplifiers are superior over single-ended amplifiers in terms of distortion and performance. So here the competency expected is to use discrete electronic devices and voltage regulators, and relevant course outcome is to use BJT as high power amplifier. Practical outcome is to build or test performance parameters of class B push-pull amplifier using transistor. So push-pull amplifier are commonly used in situations where low distortion, high efficiency and high output power are required. The basic operation of class B push-pull amplifier is similar to that of the class B, but here two transistors are used. The signal to be amplified is first splitted into two identical signals of 180 degree out of phase. The class B push-pull amplifier is almost similar to class A here, push-pull amplifier, and the only difference is that there are no biasing resistors for a class B push-pull amplifier. And class B configuration can provide a better power output and has higher efficiency up to 78.5. I heard since the transistor is biased at the cutoff point, they consume no power during idle condition, and this adds to the efficiency. The advantage of class B push-pull amplifier are able to work in limited power condition with absence of even harmonics in the output and simple circuitry when compared to the class A configuration. Now this is the observation table. We have to note down the input resistance. Input resistance is measured by at the input of the transistor, class B amplifier transistor, using a multimeter, and similarly output resistance is measured as 123 by keeping the ohm meter or digital multimeter at the output of the class B amplifier. And we had to note down the input voltage and output voltage, and thereafter calculation part. So at 5 volt, initially we are setting at 5 volt. So this is the supply VCC. As per procedure here, we have to set the VCC at 5 volt. So this is the circuit. Here this is 558 and this is 547 or 8 can be taken. Here we have taken 748, and this is the coupling capacitor, the first coupling capacitor to the first transistor base, and second coupling capacitor for the second transistor, and these two are the resistors in between the base 1 and base 2. So these two resistors are connected, and down here we see the collector, that is grounded, collector resistance, and collector terminal is grounded here, and base is connected to the input supply from the function generator. And here we see this is the second transistor or the upper transistor, and down here we have the 100 microfarad that is 100 picofarad capacitor connected, and this is the load resistance of 1 kilo ohm connected, and we are giving the input at the base of the transistor and is splitted up and provided to the base of the first and base of the second through these coupling capacitors as per the circuit. So here we have this input is divided between base, it is applied to the base of first and the second through these coupling capacitors, and output is taken through the third capacitor across a load of 1 kilo ohm. So this is the 1 kilo ohm resistor, and we have connected the second channel of the CRO2 across the load resistor, and input is connected to the base of the transistor with respect to the ground here, the black crocodile clips here. Now to take the readings, we have given 161 kilohertz, and that is shown here on the first waveform, shows the input signal to the base of the transistors, and the second channel we see distorted at these points, crossover points we see distorted. This is called the zero crossover distortion. This is due to the one transistor turning off and another taking some time to turn on. So this crossover distortion has to be eliminated, and that is the major drawback of this class B push-pull amplifier. So output we noted, it is in one division, and one division is of 10 millivolt. So here we have noted down for input of DC input of 5 volt, output is 10 millivolt, and P input DC power can be calculated as input, that is 5 volt square divided by Ri, means 3.3 kilo ohm, 33 kilo ohm, it comes 7.57 milliwatt, and output is calculated as output voltage, that is 10 millivolt square divided by, it is 123 as RO. So we get this value 0.0081 milliwatt, and efficiency is calculated. Similarly, we are calculating for the 10 volt input, output remains the same, and the input power has increased 30.3 milliwatt, whereas output remains the same, and efficiency we are getting 0.26. So efficiency is written 0.26 for the 10 volt rating. So here I can show you for a 10 volt input what is the output. So it is 10.2 for 10 volt. The output remains here in one division, and one division is of 10 millivolt. So that's it. Thank you for watching this video.